All right. Well, let's get started. Good afternoon, everyone. I'm Mark Lewis, the Executive Director of NDIA's Emerging Technologies Institute. And thank you all for joining us. Thank you all to all of our attendees for your support of NDIA and ETI, and especially for participating in today's webinar, which is entitled Nuclear Fusion 101, and will be presented by Dr. Heather Whitley from the Lawrence Livermore National Laboratory. This webinar is part of our Tech 101 series, where we try to distill complex technologies into introductory webinars, and our focus is on their national security impacts. So as our understanding of the structure of the atom was developed in the early decades of the 20th century, it was realized that the energy associated with nuclear processes could potentially dwarf that of any known power source. And of course, we know that controlled fission, the result of heavy elements fragmenting into smaller elements, has been successfully achieved, and today accounts for roughly 10% of the world's energy production. About 450 reactors operate around the globe as we speak. But if the process that powers the sun and other stars, nuclear fusion, which is the combination of smaller elements than the larger ones, can be replicated on Earth at an industrial scale, well, it could provide virtually limitless, clean, safe, and affordable energy, potential to meet the entire world's demand. But this isn't just a technology for commercial power production. Rather, the potentially limitless power of fusion could have significant military applications. Researchers have been working on nuclear fusion for decades, but there was a recent breakthrough at the Lawrence Livermore National Laboratory that has brought this technology back to the forefront, and why we thought it was a timely subject for today's seminar. It has once again reignited conversations about the possibility of fusion as the energy source of the future, but also we want to explore some of the applications for national defense. So it is a special delight that our guest speaker will be helping us understand what this recent accomplishment means and what its implications are for the Department of Defense. Let me begin with a few administration remarks before the seminar starts. First, all attendee lines are muted. If you have a question during the webinar, please submit your question in the question box in the webinar panel that you will see in the right-hand side of your screen. We will do our best to get through all the questions during the question and answer period. No guarantees, but we certainly will try. We are recording today's webinar. That's for members who are unable to attend, and also for any of you that are listening to the webinar in real time and may wish to review the material at a later date. And within the next few days, we will post the recording, slides, and answers to the question and answer period to NDIA Connect for your review. And now, without further ado, I'd like to introduce our speaker, Dr. Heather Whitley. Heather is the Associate Program Director for High Energy Density Science, HEDS, in the Weapons Physics and Design program. She is responsible for providing technical oversight and management of the design, execution, and analysis of experiments at the National Ignition Facility and other lasers. Prior to this role, she served as a detailee on assignment to the NNSA Defense Program's Office of Experimental Sciences. Dr. Whitley completed her graduate studies in quantum systems at the University of California, Berkeley, prior to joining Lawrence Livermore National Laboratory as a postdoctoral researcher, a job that she began in September of 2007. She was hired as a permanent staff member in August 2010, was a recipient of the 2011 Presidential Early Career Award in Science and Engineering. Her work at Lawrence Livermore National Labs has broadly supported the physics, data, and modeling needs of nuclear warhead studies and high energy density experiments. And she was awarded the National Nuclear Security Administration Defense Program's Award of Excellence twice in 2018. So without further ado, Heather, thank you so much for joining us today, and I'm turning the floor over to you.
Thank you so much, Mark. All right, so I'm going to get my PowerPoint up. Hopefully everything works. All right, so thank you so much for the introduction. It's a pleasure to be here to speak with you today about this very exciting topic and this breakthrough at our lab that has really energized the entire community, no pun intended. So what actually happened was that in an experiment on December 5th, 2022 at the National Ignition Facility, we successfully exceeded the threshold for fusion ignition in the laboratory for the very first time. What this means is that we delivered 2.05 megajoules of laser energy to a capsule And I will explain what all of these words mean later in this presentation. And that was sufficient to compress the capsule such that we got enough fusion out of that capsule that we had a target gain of 1.5. And what that means is that we got about 3.15 megajoules of energy out of that capsule. This is really exciting for us because it's the first proof of principle of controlled fusion in the laboratory, and it opens up new regimes for weapons physics studies, in addition to setting the stage for new fusion energy possibilities. So some of these units I realize may not be super accessible to folks, so I thought it would be helpful to kind of give a food analogy. And in talking to Mark before this seminar, we talked about the donut equivalence, and that kind of spawned the question for me: is there some sort of concept of conservation of carbs that perhaps is present in physics? But in any case, the donut equivalence of the NIF laser, what we delivered to the target, was about 2 glazed donuts, or about 489 kilocalories of energy. And what we got out was like an apple fritter plus a donut. If the donut analogy doesn't quite work for you, I also put together a TNT equivalent. So essentially, we delivered about a pound of TNT worth of energy from the laser into the target, and we got out about 1.5 pounds of TNT equivalent. So just a short outline of the talk to kind of orient you as we're going through this. Some parts of this will be more technical than others. Stick with me, I promise I'll bring it back together. So first off, I'll talk very briefly about how we got here, the history of fusion and lasers and the National Ignition Facility here at Lawrence Livermore National Lab. I'll talk about why fusion is difficult and how we would use it for energy, giving you some background on nuclear physics 101, the difference between fission and fusion, going into a little bit more detail about our ignition experiment, and then talking a little bit about energy security and sustainability, specifically how we would use fusion for energy. Then I'll get into what this means for our nuclear deterrent, talking a little bit about how we use this for our stockpile stewardship program and applications of ignition at the NIF and some of our plans beyond ignition. So first off, if you notice my background, you may be thinking, what the heck is she doing on the Starship Enterprise? I wanted to confirm for you, yes, I am indeed sitting inside of the engine bay right next to the warp core, also known as our target bay here at the National Ignition Facility. This is actually a really nice photo because you can actually see these entrance ports where the various laser beams come into this target chamber, which is this massive spherical ball. These guys standing here kind of give you an idea for how big this thing actually is. And yes, they did in fact shoot that movie at our laser. All right. So uncontrolled fusion was actually achieved on Earth for the first time in thermonuclear bomb tests over 70 years ago. Back in the early 1950s, both the US and what was then the USSR successfully detonated thermonuclear devices. And this really set the stage for what became the Cold War over the subsequent decades. So with fission weapons, there was a limit to what could be achieved in terms of their output because they have to be assembled in such a way that the mass is not critical. And with these thermonuclear types of devices, this really expanded the range of what either nation could do in terms of its nuclear stockpile. It really moved, in my opinion, moved the Cold War into a much scarier place of these very massive nuclear weapons. Again, that kind of set the stage for what we went through with the USSR and the Cold War in the subsequent decades. Now, this is an example, again, of uncontrolled fusion. We can't use these bombs for energy production. And what we did in the lab on December 5th was the first time that anyone has ever created a controlled fusion reaction with net energy gain here on Earth. So really, these fusion experiments actually sort of had their birth with some of that weapons testing that was going on back in the 1950s. So not too long after those thermonuclear weapons tests were completed, a physicist named John Nuckolls first proposed the concept of inertial confinement fusion, proposing that perhaps fusion would be possible with net energy gain in the laboratory, and in fact proposing that perhaps lasers could be used to do this. In the subsequent decades following the invention of the laser in 1958, Lawrence Livermore continued to work with our national and international partners to develop laser technologies to really get to high energy our high power laser systems, with the National Ignition Facility now being the culmination of those many decades of laser technology. The NIF came online back in 2010, was when we started doing shots. The groundbreaking actually took place in 1999 for the NIF. It took us about a decade to build the current facility, and in the 13 years that we've had since the construction of the NIF, we've used it to push the forefront of astrophysics. We've used it to do a lot of tests that support our stockpile mission and obtain data to help us understand the universe around us, and also help us understand the physics that's relevant to understanding our stockpile. Now, in these very recent years, we've really, again, achieved leaps and bounds in terms of what is possible in the lab by first creating what is called a burning plasma back in 2020, then moving on to a shot back in August of 2021 that we were super excited about, where we achieved ignition based on something called the Lawson criterion. And again, moving on to where we're at now with the 3.5 or 3.15 megajoules in target gain greater than 1. I just want to emphasize that this is really the result of decades of passion, hard work, and learning by many, many people. Thousands of people literally have contributed to these efforts. And another interesting thing that I'll come back to in this presentation as well is that really the construction of the NIF sort of started at the beginning of what we call science-based stockpile stewardship, which is the era that we live in now, which has followed the end of underground nuclear tests. So I wanted to quickly define what high energy density science means, because this is going to be a phrase that comes up multiple times in this presentation. Essentially, high energy density science is a field of physics that sits at the intersection of a bunch of different fields, including nuclear physics, condensed matter physics, and atomic physics, for example, astrophysics. And what high energy density science really is using high energy drivers like lasers to create these very high pressure conditions in laboratory, so that we can study the physics that's relevant to stars, the core of the Earth, inertial confinement fusion, which we've talked about, fusion energy, as well as doing the science that's needed to support our stockpile mission. So into the NIF. This is a beautiful photo. Most days at Livermore actually look a lot like this one. So this is a great photo, but it also is representative of our lab. It's a great place to be. NIF is the National Ignition Facility, is the world's largest and most energetic laser. And again, it enables the study of matter at high energy density conditions. NIF is about the size of 3 football fields. It's quite large. It delivers fast pulses with about 1,000 times more power than the US electrical grid. It can create matter temperatures that are up to 10 times the temperature of the core of the sun. The radiation temperatures that we can produce at the NIF are about 1,000 times hotter than the surface of the sun being colder than the core. We can create very high densities, around 100 to 1,000 times solid. What that means is I take a solid material and I compress it by a factor of 100 to 1,000 times, and pressures of up to 100 billion times Earth's atmospheric pressure, which again gets us into that high energy density regime. And we also, with this high power laser, have a full suite of diagnostics, more than 120 and counting available at the NIF. This is a photo of the facility. Essentially, I don't know if you can see my cursor, but these very long areas here, these are the laser bays where we take what starts out as a laser pulse that's like a billionth of a joule, and we amplify it up to deliver that final 2 megajoules on target. And these are photos showing the very, very small target. So the laser comes out of these 2 laser bays. There's 192 beams that get redirected into our warp core, or the target chamber, in those ports that I showed you in the photo of the Star Trek movie. So that's the laser going into this target chamber, and inside the target chamber, those lasers are focused down on this very, very small target. Now, we have a lot of great movies. I kind of wanted to put one in this presentation, but with the way that Zoom works, I was worried that the lag would not work well for me. So I just want to point out that if you want to see some of this in action, we do have a YouTube channel for the lab, and within that, the playlist, you'll find a playlist for the National Ignition Facility. All right, so again, we're taking 2.5 megajoules or 2 donuts worth of energy, and we're concentrating it in this very small target. This is a little gold can called a Holram. It's about the size of a fingernail. And inside of that, we place this little diamond capsule that's the size of a peppercorn. And all of that laser energy is driving that very, very small mass. So again, going back to donuts, we can think about donut energy to power equivalents. Okay, so if I eat 2 donuts, I can go and jog for 5 miles in an hour, and that essentially burns up the 2 donuts. And I'm operating at a power or use of energy per unit time of about 600 watts. In contrast to me, the NIF's peak laser power is around 500,000 million watts. That's a lot of zeros. That's 500 terawatts for those who like more practical units than this one here with many zeros. Now, we took that power and we put it into this target, and that target produced 3.15 megajoules over 100 picoseconds. It burned up really fast. So that had a boost in power over the initial NIF laser of like another 3 to 4 orders of magnitude, or a factor of 10,000. And just for reference, the US electrical grid peak capacity is about 1.2 million megawatts, or this large number you see here. And the point I want to make here is that both the rate of production and the amount of energy matter, and the amount of mass matters. So high energy density, again, it's because we're putting a lot of energy into small amounts of material really fast. All right, so why is fusion so hard to achieve, and how would we use fusion energy? So first of all, I just wanted to mention fusion energy is attractive for many, many reasons. It's projected that the net energy use globally is going to increase by up to 33% by the year of 2040, which means that now more than ever, it's important to find safe, carbon-free, sustainable ways to ensure our energy security and to help to support that bigger baseload global demand for energy going into the future. Fusion is a great option here because it has no geologic storage issues. It's carbon free, and it's much safer than fission for reasons that I'll talk about. Although I do want to point out that fission energy is actually very, very safe as well. So a primary advantage with fusion is that there's no storage issues related to storing spent fuel when it's done with its lifetime in the reactor. All right, this is probably the most detailed technical slide that I have. The main point I want to make here is that fusion produces more energy per unit mass than does fission. Fundamentally, the way that we use the energy of the atom, or nuclear energy, is that we do nuclear reactions. This is sort of similar to chemistry. You're very familiar with the way that our bodies use food to produce energy and the way that we can burn fuels like wood to produce energy. This is very much the same type of process where we're taking reactants and we're producing products. In combustion, we're taking wood and oxygen as reactants, and we're producing carbon dioxide and water as products. And we release energy in that process. Same sort of thing here. So with fission, what happens is we have very, very heavy atoms like uranium or plutonium that can split to make smaller particles, and as they produce smaller nuclei, they release energy in the process. On the other side of the periodic table, we have very, very light elements like the heavy isotopes of hydrogen, deuterium, and tritium, which can undergo what we call fusion reactions, which is when 2 very light atoms come together to make a heavier atom, and they release energy in the process. Now, the arrows on this plot here, this red arrow is showing the nuclear yield available per unit mass from nuclear fusion compared to that from nuclear fission. And again, the main point is that energy released by fusion is about 4 times that of fission. Now, Thinking about this, just wanted to mention one of the reasons why fission reactors have been so practical is that once you start a fission reaction in, say, a chunk of a uranium-based fuel, for example, that initial fission reaction, this is showing an incident neutron hitting a uranium atom. You start to produce fission reactions, and each of those fission reactions makes more and more neutrons that lead to more and more reactions. This is a process called a chain reaction, which basically is how the fission reactor sort of sustains itself. Once it's put together in a correct sort of critical type of configuration, it can just sort of steadily burn and produce energy. And then we can use different methods of harvesting that energy. So this is a pressurized water reactor. The main concept here is that we use the heating of this water that is produced due to the neutrons coming out of this fission reaction, the energy coming out of this fission reaction to drive steam that can drive a turbine that makes that then can generate electricity that goes out to the grid. This is sort of analogous to a wood burning fire. It's steady, it keeps going. As long as it's held in the correct configuration, it's safe, and it will keep producing energy at a relatively steady rate as long as it has fuel, kind of like a wood fire. Now, fusion, in contrast, requires that we put a lot of energy into it just to make it happen in the first place. Now, the reason for this is that these little atoms, in this case showing here a deuterium or heavy hydrogen atom, and a tritium, even heavier hydrogen atom, they have a positive charge. So when we try to bring them together, they're like magnets with like polarity, and they want to repel each other. So it takes a lot of energy to bring those close together. Now, once we get them close together, the nuclear strong force can take over, and then they undergo this reaction to produce a helium nucleus, which now has those 2 protons and 2 neutrons, and they release 1 neutron. And there's some energy that's released in this process, and the energy is carried away by this helium nucleus or alpha particle and the neutron that's produced by that reaction. So again, main point to make here, creating a burning plasma in the laboratory requires high energy density conditions. We have to put a lot of energy into material really quickly to get to this state. Now, the way that we did this at NIF in that successful fusion experiment, it's working exactly using this deuterium and tritium reaction. We drove those 192 laser beams into this gold canister that we call a holrum. As those lasers interacted with the gold, they made X-rays. The X-rays interact with this little spherical peppercorn-sized diamond capsule in the center of this holrum. And as they interact with that, they basically cause the diamond to explode. It's like a whole bunch of energy going into the diamond all at once. It vaporizes it, causes it to explode. Due to conservation of momentum, as some of that diamond blows out, it pushes back in on the center of the diamond capsule. So then that drives a very strong shock wave and a spherical compression in the capsule, so that we take this initially about 2 millimeter diameter diamond capsule, and we condense it down by about 35 times, so that it's very, very small. This goes in with a very, very high velocity, a very, very fast velocity, so that it compresses really, really hard. It heats up this deuterium and tritium to conditions that are consistent with what is in the core of the sun, and then they start to fuse. And as they start to fuse, they release helium and neutrons. Those helium atoms, in order to get to ignition, those helium atoms have to redeposit their energy into that burning plasma. So the way that we do this, we have this cold layer of deuterium and tritium fuel inside the capsule. And as those alpha particles start to get made, if we've compressed this enough, they can deposit their energy back into the fuel. And so it starts to bootstrap and heat up. So then it starts to look a little bit more like fission, in that we're having the reactions feed into more reactions. Now, one thing to mention here, Einstein Einstein's theory of relativity, E equals mc squared, is really why we have that energy coming out of that nuclear reaction. The mass isn't quite conserved when we go from a deuterium and a tritium atom or nucleus combining to produce helium and a neutron. And so that little tiny bit, 0.02 mass units of mass that is not conserved in that reaction is what produces this 17.6 mega electron volts of energy that comes out in the helium and the neutron. Now, a fusion, if you can do fusion on 2.2 pounds or a kilogram of deuterium and tritium fuel, that's the energetic equivalent of burning 330,000 barrels of oil. And again, I wanted to point this out because this really indicates what the potential for fusion energy truly is. This is huge if we can figure out how to make it work. Now, the thing about fusion, though, is that because you've created that very high energy density state, it's unstable and it wants to come apart. And as those helium nuclei deposit their energy, they're just heating up that fuel even more, so it wants to come apart even more. So this is sort of more like a detonation than a wood fire. And part of the goal is really to try to make this more like a wood fire so that we can harvest the energy from it more efficiently. So this successful ignition proof of principle, it's sort of like the Wright brothers moment for us in terms of having that initial flight. It wasn't going to get us anywhere, but with enough investment in engineering and innovation, we should be able to move this forward into a technology at some point in the future, probably a decade or longer into the future to get to that point. That being said, inertial confinement fusion, as we've achieved it at the National Ignition Facility, is incredibly important because it provides us with the scientific tool for understanding what is actually necessary for fusion energy and also to support our high energy density science in astrophysics and science in support of the stockpile, as well as other fields. Okay, so this is a slide basically to communicate that there's multiple ways of achieving nuclear fusion. The stars do this via gravitational confinement, and they operate at much higher densities and lower temperatures than do our terrestrial ways of producing nuclear fusion, including magnetic confinement or the tokamak. This is what ITER is based on. If you've heard of ITER, it's a facility in southern France where they're pursuing magnetic-based fusion energy, and it's a consortium of 35 different countries involved in that. So really, it's a huge project. The magnetic confinement really lasts on the scale of seconds, whereas stars last for hundreds of thousands of years. Inertial confinement fusion, much faster than a tokamak. It's operating at very similar temperatures to where the tokamak operates, but at much higher densities. And it's over much faster. So the key message I want to give you here is that confinement takes us towards making fusion more like a wood fire. If we can hold the plasma together and keep it stable and keep it burning, then we can start to harvest the energy using something like a steam engine spinning a turbine, just like we do for fission energy. This is a slide essentially just to show kind of what those concepts look like. I'm showing here a laser-based inertial fusion energy concept that uses a fast injection of fusion targets and a very high efficiency laser driver to create fusion that would then heat a lithium blanket. If you use heat transfer, essentially, again, whatever you're using here to transfer that heat can then be converted into mechanical energy in a turbine, which can then power or supply the grid via an electrical generator. Same concept with the tokamak. Essentially, the heat exchange would happen in the walls of this tokamak, and then there again would be a power conversion system to turn this into electrical power. Now, with all of this being said, there's many challenges to making this cost effective and efficient enough to really supply energy. However, the Department of Energy is partnering with with industry, to advance these technologies during this very exciting time, where we've now had this initial proof of principle that this is in fact possible. All right, so that was a lot about nuclear energy and fusion energy in particular. You're all experts now, or at least know enough to talk a little bit about it, I hope. So I wanted to talk a little bit more about how we're using ignition to support the deterrent. Okay, so the backdrop to the construction of NIF really was that cessation of underground testing. In 1992, the US stopped doing underground nuclear tests. And part of the promise that we made to the country when we did that, and to the world that we did that, is that we would be able to maintain the safety, security, and reliability of our nuclear stockpile using science-based tools. And our science-based tools include supercomputers and multi-physics codes that run on those supercomputers that we use to actually assess our nuclear technologies, coupled with an expert workforce and coupled with actual experimental capabilities that would enable us to continue to get data that's relevant to understanding nuclear weapons, and even higher quality data than what we could get via underground tests. So again, the National Ignition Facility is a really important part of that experimentally based part of our national security mission to support the stockpile. We use the NIF to look at a variety of different experiments, ranging from understanding the properties of plutonium and how aging impacts plutonium, up to understanding radiation transport through various different environments. And we can also use these same kinds of conditions to study astrophysics. So this helps us to understand both the origins of the universe and the evolution of solar material, and it also helps us to maintain the safety, security, and reliability of our deterrent by training our workforce, improving our codes, and really doing experiments in the high energy density regime. This is one of a handful of places on Earth where we can do this. All right, so ignition is really exciting for us within our stewardship mission because it opens up a whole range of new possibilities in terms of experiments. Now, those experiments that I mentioned where we're studying materials properties of plutonium, we don't use fusion for those at all. Those are solely laser-based experiments. There are other processes, though, and other types of questions that we have in relation to weapon science, where using the yields produced at NIF, we can move from a regime of studying isolated physics up to advanced experiments and then integrated experiments at full weapons conditions using this ignition capability. On this plot, boost physics being one example of that, where we're at now, we can do isolated physics experiments. In the future, we will do more advanced experiments, and eventually we can do experiments at full weapons conditions on a future facility that goes to even higher yields than our present day NIF. Another example is survivability, and I will give a concrete example of this in a couple of slides. That was interesting. Okay, sorry, I am not sure where my slide advanced. So in survivability space, where we're at right now with ignition, we can do component tests. We can look at small pieces of material going up to higher yields, expands our ability to test the response of materials in the warm X-ray regime. And at even higher yields, we can start to do full system testing, where say we would take an entire satellite or other object and expose it to radiation outside of a fusion ignition source to see how it responds. Now, on our December 5th experiment, we did in fact do an experiment for our weapons program in addition to that inertial confinement fusion experiment. We were qualifying a piece of hardware we call it a snout because it sits in close to capsule, it's just what it's called. We were fielding a piece of hardware that's designed to hold samples of different materials for radiation effects experiments. Now, this is the front of the hardware here. It's made of stainless steel, and you can see how there's some ripples in the front of the target or of the front of the hardware. that's due to essentially the blast wave of X-rays and material that came off of that ignition experiment as they hit this snout. There's even some little pieces of gold here from the explosion of that hohlraum. And inside of this snout, we have these little sample containers that are designed to contain different materials. And we can wire those up to different probes to do both in situ testing, and we can take out the samples after the fact and do ex situ or after the experiment testing of the materials to see how different materials respond to neutron irradiation in these environments that we can produce using these ignition capsules at the NIF. And this link here points to an actual article about this experiment where you can read about it in a little bit more detail. But what was really interesting was that inside of this particular experiment on December 5th, we had fielded depleted uranium samples. And those were coated with a gold coating to prevent oxidation of the uranium. And this is what the samples looked like before the experiment. This is what it looked like after the experiment, where the gold actually popped off of the uranium, in part possibly due to the heating of the depleted uranium due to those neutrons impinging upon it. So one important aspect of doing these types of experiments is that we really are recruiting and training the next generation of stewards, training folks to know how to do these experiments, ensures that we have the experimental capabilities that are needed to continue to maintain and support and develop our deterrent into the future. Our ignition facility, our ignition experiments, and continuing to push the envelope on that helps us to ensure that we maintain preeminence in weapons science, technology, and engineering, which again is part of our stockpiled stewardship mission. And we are supporting energy security at the same time. So what's next for the NIF? All right, so more neutrons, more yield. So actually, we haven't reached the full potential of the NIF at this point. We're actually going into a phase right now where we're going to be doing some sustainment on the facility. It's been operating at a rate of about 400 shots per year since we started, since we first started about a decade ago. There's some maintenance issues that we need to take care of. And then beyond that, we're going to start to look at an increase in power and energy to get to even higher yields. The NIF as it currently stands is built for yields up to sort of the tens of megajoule range. So going to hundreds of megajoules really requires a new facility. And we will continue to use the National Ignition Facility along with the Z-Pinch facility at Sandia to understand what we need to do to explore even higher yield, higher gain regimes in the future and look at what the next facility might look like. Now, just a comment on sustainment. I mentioned a decade worth of operations. We have some aging in the laser itself, and we also, given that we started construction on this in the late 1990s, some of the technologies that we had available when we first started are much better now, and so we'd actually like to update those and catch up on some of the deferred maintenance that comes along with operating a facility 24 hours a day, 7 days a week to do experiments. Another thing that we're dealing with now is that as we get to higher yields, we actually have to consider how those higher yields impact the facility. So we're going in and we're doing different types of sustainment activities to make sure that we can ensure the reliability of the facility and the facility's survivability into the future with those high yield shots. So in conclusion, I just wanted to mention again, this achievement of ignition really is sort of a once in a lifetime sort of scientific achievement. It's a really big deal for our laboratory, for Department of Energy, for all of our partners, and really for the world as a whole. I think this is the successful achievement of a grand challenge we've been pursuing for about 60 years. And it's really opening up many, many doors in terms of what we can do for our science-based stockpile stewardship program, as well as fusion energy. And, continuing to maintain this will ensure that we maintain our cutting edge of science, technology, engineering, and workforce well into the future. And with that, I really just wanted to mention that, again, this is literally thousands of people who have contributed to the success, and we have many, many partners all over the world. And Livermore couldn't do this without any of our partners. So thank you.
Heather, thank you so much, and wonderful presentation, and the questions have already been rolling in. So normally we like to get to all the questions, but we got a lot of questions. So I'm gonna plow through. So let me start in the order that they've arrived. Oh, first question is, what is the outlook for making that 3 football-sized mechanism smaller? Is there a possibility for shrinking it down?
Sure, absolutely. And that's a great question. So actually, again, because this was built on 1990s laser technology, using something called laser glass to build the laser, just moving to current state solid lasers would drastically shrink the footprint. So solid state lasers nowadays are much, much smaller than this massive, contraption that we need for the system that we have now. So even within the footprint of the current NIF, if we upgraded to solid state lasers, we could have substantially more energy just by virtue of the fact of being able to fit more laser into the facility.
Great. Here's a question. Actually, we got 2 questions that are similar, so I'm going to combine them. And that is, we all know about some of the risks of fission power. For example, Chernobyl, 3 Mile Island. What are the fusion risks? Can it unleash a mini sun if things go wrong?
So that's a great question. I think that, you reminded me of this anecdote from the Manhattan Project, where I think it was Enrico Fermi who was going around taking bets on whether they were going to blow up the atmosphere or not, or ignite the atmosphere when they did the Trinity tests. In any case, fusion is way, way harder than fission, and there really isn't a scenario that we know of in which you would just have like runaway fusion in the same way as you can get runaway fission. It's just not physically possible based on what we know today. So I really don't think that that's a concern for fusion.
So what about waste products that might come from fusion? And how do they compare to fission reactors?
Sure. So with fission reactors, what you end up with at the end of a fuel rod cycle is essentially something that has to go underground. It has to go to the WIP site in Carlsbad, New Mexico, or someplace where it stays for all eternity, because it's this incredibly toxic, incredibly radioactive object that basically we don't know what to do with other than bury it. With fusion, obviously, we're creating radiation, we're creating neutrons. Those activate materials, and inside of the NIF we have a lot of shielding to make sure that those neutrons aren't just going out and interacting with everything in the environment. After the ignition shot, we had to let the target chamber cool off for a few days before anyone could really take anything out of it, because those objects get activated. But the thing about that activation is that it's short-lived, and basically you just have to wait, and it sort of goes away on its own because it decays down into more stable isotopes, and then it's safe to handle, and it doesn't have that waste storage problem that fission has.
Very good. Here's a question. I guess we're the Emerging Technologies Institute, so I love when people ask questions about combining those emerging technologies. But here's one: do you think that at some point fusion would be a viable power source for directed energy weapons, high energy lasers, high powered microwaves? And if so, what would have to happen before that application could come to fruition?
So that is a very interesting question. So let's see. I know that the Navy does have some laser-based systems right now where they use, there's some articles about their laser system where I think they use a laser to shoot down a drone in a test recently. Getting back to some of that energy per unit mass stuff that I talked about earlier on, lasers deliver very high power pulses, but the actual amount of energy is relatively small when we think about the donut equivalents, right? And so that in some ways limits what can be done with lasers. And I'm not a directed energy expert, and so I'm just going to leave that question for a different discussion on a different day. Are you frozen? Can you hear me, Mark?
Sounds good. Understandable.
Okay.
Here's a question about the fuel that goes into a fusion reactor. So yep, I can hear you. Can you hear me?
I can hear you.
All right. So we have a question about the fuel. The question is, you touched on it a bit, but the questioner is saying they've read that the fuel availability for fusion, including tritium, is cited as a significant limiting factor. Okay, so the question is about the availability of tritium as a fuel, and is it as a potential limiting factor for commercial fusion production? Can you talk to the issue with tritium, and are there alternate fuels and availability?
Sure. Yeah. I mean, there is an issue with tritium availability, and I think tritium is something that has to be bred essentially, like in a reactor. Potential alternatives, there's a lot of different light ion fusion reactions that are potential alternatives. I think folks have looked at boron and lithium, for example, based reactions. And I'm actually not a nuclear engineer, and I don't have much more of a well-informed answer than yes, it's been looked at. I am not aware of a demonstration of it though, where it's actually, sort of being pursued in earnest as a commercializable technology.
Yeah. Heather, I don't know if you can still hear. We lost you there for a minute. All right, so
I can
here's
hear.
a question about the. Okay, here's the question of the very high temperatures and pressures. So they're short duration, but what are the implications for materials? Do you have to worry about structural integrity of the reactor, for example?
Sure. I think that is one of the engineering challenges that would have to be understood and overcome. Now, one thing about the radiation that's produced being neutrons, so essentially you want to use those to heat up something and then harvest that heat to turn a turbine, right? And so they're not going to be the neutrons, you're going to be catching them in this thermal blanket, whatever it is. They're not going to be flying around everywhere in the facility. And most likely you would have shielding to make sure that you're not just continuously degrading the structure of the.
All right. As you know, there's tremendous concern about advances in other parts of the world, peer competitors, including Russia and China. And one of our participants wants to know, are the Chinese and Russians also working on fusion? And if so, do we know anything about the status of their research?
So the Chinese do have a laser facility called their Shangguan laser, and they publish papers about their activities on those laser facilities. And so we can read about their papers. With respect to what are the Russians doing, I actually don't have an answer for you on that. I'm not sure. So I'll elaborate there a little bit. So for the Chinese, what they've published, a lot of their technologies look quite a bit like ours, and their design concepts look quite a bit like ours. And with, inertial confinement fusion fundamentally being an area of unclassified research, of course, we publish lots of papers. So it's not really a surprise that that the concepts would be similar.
All right, no, that makes perfect sense. Here's a question from someone who says he wishes this work well, but I'll read the question. The individual writes, about 63 years ago, as a freshman engineering student, so we can do the math how old the gentleman is, I toured the Matterhorn fusion project at Princeton's Forrestal Research Center. The scientists there claimed to have had sub-microsecond sustained reactions, and they said commercial operation should be in about 50 years. That was 63 years ago. Subsequent prophecies have maintained that 50-year forecast. So how confident are you in future year forecasts? And the questioner says, by the way, I do wish you well. So he's an enthusiast, but we hear this a lot about fusion. It's always 10 years out or 30 years out or 50 years out.
Of course, yeah, and I have a little bit of his sentiment as well. I will say my expectations tend to be very strongly tempered by what we've seen in the past, right? I think so. What do I think the actual time horizon is? I think that's a very hard question because what I've seen, I think, in the history of innovation is that a lot of the time, once there's sort of a big breakthrough, if there's enough investment and enough sort of engineering spin up all at once, you can really move things forward much more quickly. I would say that up to this point, we were still in the phase of even figuring out what was possible, right? And again, not everything is like roses and daisies and happy in science. When we went into the National Ignition Campaign back in 2010, we ultimately failed, right? The expectation was that the NIF was going to produce fusion and produce ignition straight out the gate, and it didn't. And 2012, it didn't, right? 2020, it didn't. Lo and behold, 2022, we got there. But that was after perfecting so many different things with respect to the laser delivery, the fabrication of targets, the design of the implosion. All of these things really had to come together. And I think in order to get to that point of a commercially viable source, we have to figure out how to back off from those standards of perfection, but still have the ability to produce something like an ignition capsule. And so I think that the listener's comment is well placed. It could be that we are still looking at another 50 years, right? But I think the hope is that we're looking at 10 to 20 rather than 50.
And by the way, we have other questions along those lines. Other people asking, what's the timeline? So I think you've just answered that one. So here's a question I really like from one of our participants. And an individual asks, are you actively taking your success stories to universities for show and tell to encourage students to pursue careers and supporting your work? And then comments, you're going to need a growing workforce.
Oh, absolutely. So we were already hiring before this happened. And since it's happened, we're trying to leverage this excitement about our laboratory and the work that we do here to recruit. So yes, we would love to get out to universities and give talks. And I know a lot of our staff have already been invited out to universities to give talks. If there are university folks in the audience who would like to have a seminar, please feel free to reach out to us, and we'll find the right person depending on the department and the location. We actually have, we have employees from all over the world here. And I think, even some of our staff have been invited to give seminars at universities in Germany, for example, right? So I think we are getting out and we're getting the word out. And we do recruit internationally as well, although, there is a high need to hire folks with US citizenship as well.
So another question I really like, because I'm a space guy. So we've got someone asking, are there implications of fusion power and maybe this breakthrough for space exploration? For example, we know we have in the past built nuclear thermal propulsion using fission reactors. What about fusion power for space propulsion?
Sure. I mean, that's a great question. I would say that it's definitely a technology that we would have to pursue to find out whether it's possible or not. For all of the reasons that you stated, if it is viable, it might make sense. Yes.
Very good. So now we've got a question. So you talked about the net gain accomplishment. Has it been repeatable? Have you done it again?
So let's see. So we actually haven't repeated the experiment yet. And I think the fundamental issue so far has been capsule quality. And actually between the 2021 shot to the 2022 shot where we got ignition, we did a series of different shots where we were looking at variability. A lot of which was coming just from capsule quality, trying to repeat we call it N210808 because it was August 8th, 2021, and that's how we number shots. Just trying to repeat N210808, we know that we are incredibly sensitive to capsule quality. And for our ignition shot, we actually came up in laser energy a little bit from 1.9 megajoules in 2021 to 2.05 megajoules. And that is buying us a little bit of margin in terms of capsule quality, but we're still not quite to the point where we can just snap these out one after another. I think that's the goal this year, though, is to get to.
Very good, very good. So we have time for one last question, but I'm actually going to combine two questions to try to sneak it in. And is how well supported is nuclear fusion in the latest budget request, and are you getting the level of congressional support that you think that we need in order to keep the field moving forward?
So that is a great question. So I think in the 2023 budget, we actually saw a significant increase in the NNSA defense programs budget that's allocated for the ignition or inertial confinement fusion or fusion on the whole. That largely is due to the sustainment activities that are taking place at the National Ignition Facility and at the Z facility at Sandia National Lab in Albuquerque, New Mexico. So that increase in the budget mostly is for sustainment of the facilities. I do think that we are somewhat underfunded when it comes to the R&D portfolio, especially when it comes to some of our science-based stewardship mission, where we really need to be hiring, we really need to be partnering with the ICF program in order to move new technologies forward, but our budgets are constrained. And in fact, if you look at the presidential budget request, the PBR numbers for FY 25 or so, or 24, you'll see a decrease across some of the areas within assessment science. And assessment science is a part of what funds the actual application of ignition experiments at the NIF. And so I think getting those budget numbers back up would really help our program as a whole and enable us to seize on the moment to deliver for the nation.
Thanks. And Heather, I'm going to let that be the last word. Dr. Heather Whitley, thank you so much for joining us. It's really exciting to hear about the implications of this accomplishment, what it means for the field, directly for someone who's been a leader in the effort. A great seminar. I want to thank our attendees also for their participation. We got some really good questions. I want to remind everyone we will post the recording of this webinar online as soon as possible. If you have any feedback about this webinar or the series in general, especially if there are topics that our listeners would like to see us cover in the future, please feel free to email us at eti@ndia.org. Before you go, I just want to highlight a couple of quickly some upcoming ETI events. On May 3rd at 1 p.m., we'll be hearing about the Defense Technical Information Center, DTIC, with Christopher Thomas. May 10th at 1 p.m., Agile Software Development with Forrest Scholl. On May 11th, we have the big release of ETI's Hypersonic Supply Chain Report. Rebecca Wosenberg and her team have been working on this with partners in industry and government, talk about what supply chain is necessary to supply hypersonic capabilities at scale. And then finally, we're proud to announce that we will be hosting our first annual Emerging Technologies Conference at the JW Marriott in Washington, D.C. on August 28th to 30th, 2023. It will be the Emerging Defense Technologies event of the decade, certainly of the year, and we hope to see you there. Registration information is on our website. Please feel free to reach out if you have any questions. Again, thank you, Heather. Thank you for our participants.